Dear me, I've been looking through old narrated PowerPoints. I just listened to one, I guess last night, that started with me saying that it had been many moons since I had narrated a PowerPoint. So I guess that means it had been months. At this point, it's been years since I narrated that particular PowerPoint. So not entirely sure what the appropriate phrase would be. It's been many suns, maybe, since I've narrated a PowerPoint. Um, although that kind of makes it sound like the sun rotates around the Earth, doesn't it? I don't believe that's the case. So maybe I could say it's been many Earths. I don't know. Where's Stephen Hawking's when you need him? We're only we're only on the first slide, and already this PowerPoint is blowing my mind. So let's put our astrological musings behind us and get back to statistics. Now, the overview of where we're going in the next few PowerPoints is this. We've mastered some pretty powerful ideas. Those powerful ideas are confidence intervals and hypothesis testing. I think it's really cool, right? That is, you take an introductory statistics class, right? You're maybe not even any type of math major. You're not even majoring in anything quantitative, but you take this just to build up some statistical literacy. You get some exposure to these hypothesis intervals and confidence, or hypothesis testing and confidence intervals. And you kind of like it, maybe a little bit more than you expected. It's fun, right? And so you look into our minor in applied statistics, just a couple extra classes. You could learn a little bit more. You could distinguish yourself from your peers by having the credentials of a really marketable skill set. You take those extra classes, and what are you learning? More confidence intervals and hypothesis testing. And then you get the minor, and you're like, you know what? I really love this. And all these recruiters are trying to just throw money at me and hire me, and I'm working at my job, and everyone's looking at me as this kind of like statistical rock star. Why don't I go back and get a double degree? Why don't I go back and get an entire degree, a bachelor's degree in statistics? And so now you're taking even more classes still, and what are you learning? You're learning confidence intervals and hypothesis testing. Now this little crush, this infatuation is becoming what? It's becoming more real. It's becoming, dare I say, the L word? And you decide that you need to get a master's degree in statistics. Yeah, we actually have a master's degree in statistics. We actually, Westchester has a 5-year program. 5 years you can get a bachelor's degree and a master's degree. Wow. What are you learning when you're working towards your master's degree? Confidence intervals and hypothesis testing. And now you know it's more than love. Now it's commitment. Now you want to put a ring on its finger. Now you're going full in. You're going to get a PhD in statistics. You're going to start doing cutting edge, innovative, original research. You're going to start building, sort of putting your own fingerprints on the field of statistics. And what are you inventing? New confidence intervals and new hypothesis testing. I think it's kind of cool. I think statistics is very unique in that sense, that you could actually, as a beginner student, as a grasshopper, you can understand and get exposure to ideas that like PhD level statisticians are working with. And as our second bullet point implies, these two things are really, in essence, the molecular building blocks of applied statistics. And we're going to start looking at some innovative ways of extending them. To begin with, we're going to see that they can add additional insight and depth to our earlier discussions on linear regression. So bivariate relationships, that was back at the beginning of the course. We talked about things like correlation. We talked about things like regression, coefficients of determination. We're going to revisit these ideas and talk about them in greater depth now that we have sort of a beefier toolbox to work with or to talk about. It may be worth pausing this PowerPoint. It may be worth going back and reviewing your notes, kind of refreshing your memory about some of the stuff before going further. particularly if you're taking this in the fall and the spring, when you're going to have to take a comprehensive final anyways, and part of that comprehensive final is going to require you to master that material. So why not brush up on it now, and it'll make it easier to pick up this more advanced material that we're getting ready to talk about. For those of you that were too lazy, here's a little bit of a review in a nutshell. So as we may recall, linear regression allowed us to determine a line of optimal fit, a line of best fit, we call it the least squares regression line, to some conjectured linear relationship between two quantitative variables x and y. So we made the scatter plot, we took a look at the scatter plot, we said in some cases that scatter plot looks like it's approximating a straight line. Of all the possible straight lines, what's the one best line that fits it better than any other? Now recall when we're talking about lines, that a line, this line of best fit for example, is uniquely defined by two characteristics. A line is defined by its slope and its y-intercept. They're sort of the DNA fingerprint of a line. They uniquely define that particular line. Now, in terms of what we talked about, we can think of these lines, these conjectured relationships, these platonic underlying realities as parameters. In particular, the defining characteristics of the line, the slope and the y-intercept, these now become new parameters for us to statistically study. To be mathematically explicit, the big idea is this. We conjecture a linear relationship between two variables x and y. Often that conjecture follows the creation of a scatter plot. Mathematically, the relation could be expressed thusly. Y equals beta naught, it's the Greek letter beta, plus beta 1 times x. Now, there's actually a little bit more to the equation than that. I'm simplifying it. In real life, there's not a perfect relationship between x and y. In real life, if we're looking at any variable, say using a person's height to predict their weight or a person's weight to predict their height, right, we're not going to be able to predict it perfectly. There's going to be some sort of fudge factor, some sort of margin of error. A true equation has to take that error into account. So this is a little bit of a simplified equation. There's that y-intercept, beta naught. There's that slope, beta 1. Beta naught and beta 1 are parameters. Just like mu, the population mean, is a parameter. Just like sigma, the population standard deviation, is a parameter. In fact, it's sort of statistical convention we can maybe see and appreciate now to use Greek letters to signify parameters. The weird sort of odd letter out is using the letter P, not a Greek letter, for population proportion, isn't it? It's this weird sort of kind of glaring anomaly. And in some practices, not introductory textbooks, but there are more advanced textbooks that actually refer to a population proportion as pi, using the Greek letter pi, which kind of preserves this this convention of Greek letters for parameters. So again, we have this sort of population relationship, this quote, let's call it a true linear relationship. And it's defined by this beta naught and this beta 1. These are parameters that we would like to in some way estimate. So how do we actually go about estimating these parameters? Well, we already know the answer to that question. We have formulas. They're in our textbook. But even better yet, our computer knows those formulas. Formulas are also living inside of our computer, or at least a software package that lives within our computer. And the computer uses these formulas to come up with this sort of optimal line, this line of best fit, this best guess, and we call it y hat to distinguish. It's like our best guess. And we use not the betas, but lowercase b, so b0 plus b1x. So b0 is our best guess for beta naught, b1 is our best guess for beta 1, just like x bar was our best guess for mu. So again, the betas are our conjectured equations, they're parameters. The b's from the previous slide, from our fitted equation, these are statistics. They're generated from a sample, right? We have that scatter plot, and we look at that scatter plot, we fit the line that best fits that scatter plot, but the scatter plot's a byproduct of our sample. And since they come from a sample, samples are random. That means that these b's, these coefficients, are random variables. They have their own probability distributions, means, standard deviations, everything we talked about before. And just like before, we can apply all of our cool inferential tricks to them. Now, there's 3 tricks that we're going to talk about in this class. Certainly more you could do if we had more time together. The first is we could do a hypothesis test for the significance of the slope. That's what this particular PowerPoint or video is going to focus on. The next follow-up PowerPoint is going to talk about the next 2 bullet points, and those are confidence intervals with respect to regression. We'll talk more about those in the next PowerPoint. So how do we do a significance test for slope? Well, again, it's always going to be this 4-step process, this rhythmic, this beautiful, this elegant 4 steps that we just love, and we keep coming back for more. Now, how do we set up our hypotheses? The traditional hypothesis for a hypothesis test of slope is this. The null hypothesis is that slope, beta 1, is equal to 0, versus the typically 2-sided hypothesis that it's something other than 0. Is that intuitive? Does that make sense? Yeah, I guess it does, doesn't it? Because we don't have it sitting in front of us, but we could probably conjure it forth in our mind's eye. If we look back at that theoretical conjectured equation, y equals beta naught plus beta 1x, what happens in that equation? Go back and try it out for yourself. What happens to that equation if we plug a 0 in for beta 1? Well, now we have 0 times x, so x goes away. When the slope is 0, that essentially removes x from the equation. Yeah, 0 is a multiplicative killer. It kills the x. And so what is that saying mathematically? It's saying that y does not depend on x. Because at the slope 0, the x goes away. There's no x in that equation. Bye, Felicia. And of course, if that slope is anything other than 0, then that's going to preserve the x, and y is some linear function of x. So this particular set of hypotheses is really saying that y is a function of x, y is a linear function of x, or y is not a linear function of x. Actually, it's a flat line. Now, step 2. Step 2 is we have to construct our test statistic. Our test statistic is essentially this. It's that B1 minus 0 over, SE stands for standard error. Standard error, we may recall, is just a fancy term for standard deviation. This is really the same formula for a test statistic than way back when we were doing hypothesis tests for a mean, right? When we were doing a hypothesis test for a mean, it was x bar minus mu naught. So our best guess from the mean minus our hypothesized mean. Here it's our best guess for the slope minus the hypothesized slope. The hypothesized slope is 0. Divided by that standard deviation. It's again looking at the distance between our best guess for the slope, the sort of sample slope. How close is that to the hypothesized value of 0? In units of standard deviations. Now, of course, subtracting 0 is not doing anything, so that's where I write that equality. The left-hand side, I put it as that minus 0 to try to illustrate or try to emphasize how it's the same type of format as what we've seen before. Of course, that minus 0 doesn't do anything, so the simplified version is on the right-hand side of the equality. Once we have our test statistic, we can show mathematically that it follows that oh so familiar t distribution. The degrees of freedom are a little different than what we're used to. Instead of n minus 1, which it had been previously, it's now n minus 2. In terms of calculating the p-values, I would strongly encourage us to not worry about using tables or anything crazy like that. In practice, we would use a software program on our computer. In fact, I'm not even going to really emphasize how to do it on our fancy TI-83 or TI-84. For something like this, a computer is going to be your best friend. And then finally, once that computer has determined a p-value for us, it's time for step 4. It's time to make a decision. Just like before, we compare our p-value to our predetermined alpha level. If the p-value is less than alpha, we reject the null hypothesis. That's always been the way we do it. In the context of this problem, they're saying that there is evidence of a linear relationship between y and x. If the p-value is more than alpha, we fail to reject the null hypothesis. There is not sufficient evidence of a linear relationship between y and x. Now, we want to be a little careful. We talked about this in some of our earlier stuff when we first talked about regression. This might mean that there's no relationship. It might also mean that there is a relationship between y and x. It's just more complex than a straight line. A curve, perhaps. So here's an example. 143 bears. And it's real data. I'm not quite sure who gathered it or where it came from. I guess someone had a dinner party with a bunch of bears, and as part of that dinner party, they measured the bear's weight and they measured the bear's length. So they have both of those, and they were interested in determining whether a bear's weight could be explained by their length. If you actually read the data set, it does talk about, I guess for park rangers, knowing the weight of a bear is important. I think sometimes they tranquilize them, maybe to move them around, and the dose of the tranquilizer is influenced by the weight of the bear. So to know how much tranquilizer to give them, they need to know how much the bear weighs. Makes sense. And I guess it's dangerous to weigh a bear. I mean, that makes sense too. I'm not sure that I would want to be the one trying to convince it to step on the scale, especially if it put on a little bit of weight. Now, I'm not entirely convinced that it's less dangerous to measure their length, but let's play along, and presumably it is. So if that's the case, maybe we have a less dangerous metric that in some way could be insightful to the more dangerous but also more useful metric, which is that bear's actual weight. So as blossoming researchers, as statisticians in the making, it's typically always a good idea to follow the principles we established early in this course. Whenever possible, try to start with some sort of picture or graphical summary. And so here is our scatter plot. Our x variable is length, our y variable is weight. If you look at that scatter plot, it looks like a bit of a straight line. There is some unusual stuff going on there. It looks like perhaps there's a little bit of curvature. It's also kind of a weird funneling out pattern, right? That is, the points are really packed together for low lengths and seem to kind of spread out or get more diffuse for longer lengths. Those are important things. And if we had the time to go a little bit deeper, if you, for example, want to declare a minor in applied statistics, we could explore some of those cool ideas, like would a curve fit this better than a line? What are the implications? Is that funneling that we're observing important? But for now, for what we're talking about, we can see that a line fits it pretty well. Again, a curve may fit it better, but a line seems to fit it well. If we use the equations to come up with that one unique line of best fit, using that least squares method that we talked about way back, the software package tells me that our y hat, our estimated weight, is negative 441.4 plus 10.338. So that negative 441 is our B0, and that 10.338 is our B1. Now let's do a hypothesis test to see whether or not that slope is something other than 0. Here's the output. There's so many different software packages out there. This one is something called Minitab. I personally don't know a lot of sort of professional statisticians or researchers that use it, but it's pretty popular within education. It's used a lot in the classroom because it's fairly easy for non-statisticians to pick it up. It's got a kind of point and click intuitive interface. And so there's the output. Different software programs give slightly different looking outputs. We can see the coefficients are part of this output. So where it says that line where it says constant, that's referring to the y-intercept. The line where it says length, that's referring to the slope. So we see there that the y-intercept is that negative 441. We see that the length is the 10.338. These are both, remember, statistics, which means they're random variables. The next column over is our best guess for their standard deviation, where it says standard error of coefficient. Standard error, again, is just a fancy term for standard deviation. They're random variables. All random variables have standard deviations. Now let's focus on that second line, the slope, because that's what we're interested in testing. Where it says t-value, we see 21.42. Where does that come from? Well, it's just elementary division, isn't it? If you just think back to your multiplication tables, your division tables, everyone knows that 10.338 divided by 0.483, well, obviously that's 21.42. Actually, we can ballpark it a little bit, right? We have something close to 10 divided by something close to a half, so it's going to be close to 20. And so our t-statistic is 21.42. That's saying that the best guess for the slope, the sample slope, is 21 standard deviations above the hypothesized slope of 0. Wowza. Oh, smoky. That is a lot of standard deviations. The p-value is immeasurably small. So we see that p-value column. The p-value is not actually 0. P-values won't be 0, but it's so close to 0 that it's sort of like off Minitab scale. And of course, the small p-value gives us our conclusion. The p-value is less than 0.001, hence we reject the null hypothesis. We conclude that there is very, very strong evidence of a linear relationship between the length and weight of a bear. A linear relationship fits it very well, fits it much better than sort of not using x at all. Again, it doesn't necessarily say that a curved line wouldn't fit it better, but alas, there's only so much time in this class.